The other issues, as I said before, NIST have published these values for this, what they call a pre-evacuation delay in this paper, but I don't think they should use the term pre-evacuation. I think it's a stairwell entry delay. But they don't give a distribution for it. So I suppose when it says average and plus or minus, you might say, well, maybe that's a standard deviation. So let's assume, in the first part of analysis, we'll say, let's assume that's a mean and standard deviation. What happens if I use that? But if I go and plot the stair entry times from their spreadsheets as a distribution, you will see that, and I've not labelled the buildings, but you get a whole range of different results. So in some cases, you get something that really doesn't look like a normal distribution. It looks more like a log normal type distribution. And that's what you might expect. I mean, for pre-movement times, pre-evacuation times, log normal type distributions are classically what you see. And some of these are. And some of these are others, I don't know what sort of distribution. And some of these might be a little bit more normal. So the fact that I might assume a normal distribution based on the NIST data, maybe it's not appropriate when you actually look at the spreadsheet and try and work out how long did it really take for each person to enter. And you can go into our friend at risk, and you can get a best fit distribution. And so you might, what I've been trying, the next stage of this work has been looking at, well, should I use the normal distribution that NIST have given, normal, or should I be better off using the best fit distribution for the data? But the other thing I can do is I've got the entry time for each individual person. So what happens if I give each of my agents in my model the exact time that I know, not just use a distribution, but use the number that's actually given to me? What difference does that make to my model? So basically I've done that here. I've just chosen one particular set of stairs. The first thing I did here was just say, what happens if you don't put any delay in at all? Well, not as you'd expect, with no delay. Again, this range here tells you the output of the model. You're going to get people exiting a lot earlier than the event, because basically it says everyone moves at once. So clearly a 0-second pre-movement delay or entry delay, it's important that you put some sort of entry delay. You can't exceed 0. And then I basically here use the normal distribution data from the NIST, and that shifts all the model pretty much on top of the data. Then I tried this particular data set here, and this wasn't really the best one because it's not particularly offset in one direction, not skewed. So that, I mean, I need to go back and do some other buildings, but the trouble is that some of the other buildings, the data about the entry time is pretty limited. But anyway, you get the result in this case that hasn't made much difference. What was really interesting when I put the actual entry time of each occupant into the model, and I was not using distribution, I got this result here. And I was quite pleased to see this. So this basically tells me that the mechanics of the movement down the stairs in my network model is working pretty well. Because I basically, because people don't enter all the stairs necessarily at equal time and equal sets of stairs, I've captured the effect that you've got these sort of delays or bumps as a group of people get out, and then there's a time lapse where there's nothing happening, and then another group of people are exiting and so on. So to see this come out of the model, the network model, I thought was, even for myself, I was quite amazed. But I'm still not convinced this network model is, I can't believe it works. Oh, it's just a network model. Why are you using FDS evac, the most complicated? Well, I don't think you need to. I think a network model does it. But anyway. So then the last thing is I went back and said, well, so we had that SAP handbook result, and we've now learned, at least in the terms of the time step, that we're going to get a slightly different result depending on what time step you use. So this is the stuff we saw before, the SAP handbook and causes result, and I basically tried different time steps, 1 second, 0.5, 0.1 second, and looked at the time for total evacuation. You'll see here that at 1 second, we've got the result I got before. I mean, this is a mean and standard deviation. And then as I change the time step, and I plotted it here, there is a shift. So there is the model says people get out a bit earlier, depending if you put a short time step. And I know the reason why that is if you use a 1 second time step, as the model calculates whether a person travels from one node to another, for 1 second time step, it rounds it to the nearest second. So I might be standing here, ready to leave the door, and it might only take me another 0.1 of a second to get out of the store to the next one. But if I'm running a 1 second time step, then it says, oh no, it's going to take another second to get out of the door. And when you've got hundreds of people with hundreds of time steps, those assumptions kind of build on top of each other. You end up with a slightly longer evacuation time because I've not captured the fact that some people will get out the door within the next tenth of a second, according to the model, not the next whole second. So that's why the time gets slightly smaller. But I thought, well, what we'd like to think is, as you make the time step smaller and smaller, we should converge on a result. So if you plot this graph here, plots the change in total evacuation time as a function of the time step. So if we normalise it and say that a time step of 1, we end up with a kind of our baseline, and then we change the time step, we reduce it by a tenth and a tenth again, so our time step gets smaller and smaller, we sort of converge, what we'd expect. So it's basically saying, you know, if I made the time step even smaller, I expect the next result to basically be the same. So we kind of get what we want. Of course, the downside of this is every time you reduce the time step by a factor, the simulation takes proportionally as long to do. So for this building here, it takes about 60 seconds to do a calculation for 2,700 people at 1 second time step, and then it takes 600 seconds for this one, and 6,000 seconds for this one, because it just takes so much longer to do all the calculations. So there's always this trade-off between time you're willing to wait for the model and, I don't know the word accuracy, but and the result you get. Because in this case, we don't know if it's accurate or not. All we know is it changes because it's